So, as I mentioned, it's like why CQRS? Well, I know, I've been developing for a long time, a long time. And if you look at my bio, I'm very honest about the fact that I built systems that weren't fast enough and were brittle and broke too much, and I didn't like it. And this is why I like things like CQRS, and this is exactly why I love things like Akka, because it gave me tools to do like high performance, high reliability systems that didn't wake me up in the middle of a night and the weekend because of a production outage. I don't like having to do those kinds of things, and I want tools that allow me to enjoy my weekends, not spend my weekends fighting some type of production outage. And CQRS, often the databases were the things that were our performance bottlenecks, and CQRS really opens things up from a performance standpoint. So it's increased throughput for definitely, because it's really, you're significantly reducing contention on the database. And it's optimized for data models. And I want to go back to a prior slide to make that point. And what I mean by optimized for data models is that, say this service, some of the queries that you want to do with this service are best served by a relational tables. So you have an event handler that's feeding events to a relational table. But say you want to do other queries using something like Elasticsearch, an inverted index type of a document query or something, almost like a Google search type of thing. And I've done this kind of thing in the past myself. Or maybe use another. It might be a hierarchical database or a Mongo, or whatever you want to use. So you can have multiple of these event handlers. Some the events. One event handler is feeding data to relational query tables. Another event handler is feeding data to, say, Elasticsearch. Another one's feeding data to Mongo. Whatever you want to do, you have the flexibility to do that, to do those kinds of things using this type of an approach. And with the Akka part adding on to it, we're stateful, not stateless, and that adds to performance as well, because you're reducing how often you have to go back to the database to read from it. So this whole concept, I like to use the terms hot state and cold state. So that's what I'll kind of wrap up with here with, is that kind of taking you through an example of a stateless flow and a stateful flow. So on the top represents code. This box in the top represents the code where computations occur. The bottom represents the data, the database. And I call the top is where hot state computation occurs. The bottom is where you store things in cold state. So when you get a request in a stateless type of a system, the request comes in. That trigger is recovering the state, reading the state from the database, you're pulling it into memory, processing the incoming request, writing whatever changes are needed as a result of the processing back to the database, and then throwing the state away. And so that's the flow. And I'm not saying that stateless is a bad a bad architectural pattern at all. It's a great architectural pattern. It's extremely mature. We have fantastic tools to do these kinds of things. But when you're getting into performance types of situations, you have to consider the consequences of using this approach. And is there a way maybe to go faster? So that's the only reason I'm showing this. Not that stateful is bad in any way. It's a great pattern. Nothing wrong with it. So anyways, another command comes in, read the state from the database, get it in memory, run your processing, save it. So just repeat this cycle where we recover the state, get it in memory, but we can't keep it there because of the nature of the way the stateless systems work. So we constantly have to go through this cycle. So it's the reads that we're doing over and over. The writes are unavoidable. When you make a change, you want to get it written to a safe place as quickly as possible, within a normal transaction. So that's the stateless flow. Now let's take a look at the stateful flow. So we still have the same thing. We had the code at the top, the cold state, the data at the bottom. Same thing though. A request comes into the system and say the state is not in memory at the moment. So we have to recover the state from the database. So we read the state from the database. Now it's hot in memory. We process that request. We write, the changes back down to the persistent store, the cold state. Now, if you're using event sourcing, all you're writing is like a single insert of an event. You're not updating or deleting or anything like that in tables, which is kind of the normal pattern with a CRUD type of an approach. So the next command comes in. Well, the state's already hot in memory. It's active, so we don't have to read it again. So we receive a command, we process it, we write the change. We receive the command, we process it, we write the change. So we've eliminated the read. So that can definitely take some load off the database, which helps because when you want to, if you're pushing a system fast and you want to go a lot faster, if you can take some load off the database, it's going to help you go faster. It's going to help the database go faster. So that's the flow here. So in that map-based Where on Earth demo app, it's built using event sourcing. Both there's two microservices and they both use event sourcing. But the first microservice, which is the simulator, which is kind of simulating IoT devices in the real world without actually having physical devices in the real world, doesn't have a query component. It doesn't need it. But the twin service, as I call it, it's planned digital twin. IoT devices, the backend is often called the digital twin of the physical device in the real world. But in any case, that microservice does have a view.